Now see, here is our laser heat flux. It is also moving with the same velocity v as our cutting tool v, right? It should move with the same velocity. So when it is moving, it will heat the surface. Heating will happen. After heating, heat diffuses into the workpiece due to conduction. That's why carefully I have shown here this region, because as time passes, this conduction depth will slightly increase, because it is a transient phenomenon now, because we are not going to model it as a static. This is fully coupled and transient simulation. With time, because laser source started from here and it is moving in this direction, as it moves up to here, till that time heat already diffuses into the workpiece. And this is very important. Later I will tell you why this depth is important. Or now also I will explain a little bit. We will call it as a conduction depth. If you don't have this conduction depth sufficient, means you will not have sufficient softened layer, so that will not take advantage of laser heating. If this conduction depth is very small and your feed is very large, let's say this is the feed value, then you will not see any reduction in the cutting forces. So there should be sufficient conduction of the heat inside the workpiece, so that sufficient up to sufficient depth softening should happen, and that softened layer should be removed by the cutting tool. Then only we can get advantage of laser assisted heating and machining. So that's why one more parameter will come into picture that I will explain in next slide. But at this slide one should remember one thing, that laser heating part is coming from subroutine, specifically VDFLUX. Now I will explain why VDFLUX. Because machining simulation involves all kinds of nonlinearity. Say material nonlinearity, because material involves all plasticity, damage, nonlinearity. Other contacts are involved. So that is boundary condition nonlinearity. And definitely there is a large deformation involved due to very high strains. So all three sources of nonlinearity, like geometric nonlinearity, contact and material, is involved in machining. Apart from this is a transient simulation. Both means heat distribution as well as, if you see, the strain rate effect is also involved. At what velocity our cutting tool will move? What is the strain rate? I already talked in last class that 10 to the power 3 to 10 to the power 4 per second. That is the strain rate. So very high. So due to all of these complexities, machining problem is very difficult to solve with implicit method. And definitely we need to go for explicit solver. And even in Abaqus, your Johnson-Cook damage model is not available for implicit because they know that such kind of softening and damage cannot be handled by implicit method. So definitely we have to go for explicit solver or Abaqus explicit. That's why DFLUX subroutine will not work and we have to go for VDFLUX because this V's, whenever this V will be there, any subroutine starting with V means it is specifically written for Abaqus explicit. And you know, if you remove V, so DFLUX is for Abaqus standard or Abaqus implicit. So that's why we have to use VDFLUX subroutine and Abaqus explicit to solve this problem. Even people have tried DFLUX sequential approach. In sequential approach, people did they simulated heat first with laser. They simulated heating first and then they take this output. So heating using DFLUX. Take this output, machining model, explicit. So do this thing, many times we lose some of the boundary conditions or convection. So better or more accurate is a fully coupled approach. In this, we are not going to do heating first and then machining like that. Simultaneously, both things are happening. Your heating is followed by your cutting tool. So this fully coupled approach is not was not known earlier. I can say because this VDFLUX subroutine was not developed by any of the researchers. Maybe before 3-4 years, most of the people used to use DFLUX subroutine. And in recent research only, you can see the name and people are using it, and they are getting very good results as compared to your sequential approach. So the good thing is that in our sessions we'll fully focus on this fully coupled approach because this is highly accurate, well accepted, and it will produce very good results. And the whole simulation, heating and cutting, we can see at in one animation, one simulation. And we have flexibility to define one very important